Welcome dear learners. We are continuing Unit 5, Inorganic Chemistry Practical 1, Volumetric Analysis. This is the last module associated with the experiment, and in this module we are discussing experiment number 13, that is estimation of copper in brass. The contents of this module are a description of brass alloy, aim of the present experiment, principle behind the experiment, reagents required for the experiment, and various procedures under this experiment as preparation of standard K2Cr2O7 solution, standardization of sodium thiosulfate solution, and estimation of copper. Finally, results associated with the entire experiment. Moving on to the description of the alloy brass, that is brass as an alloy. Brass is an alloy made of copper and zinc along with the trace quantities of other elements. Even though trace quantities of other elements are present, copper and zinc are the two major components of this alloy brass. And the present experiment is to evaluate the copper content present in a given sample of the alloy brass. Most of brass contain about 60% of copper. So, remaining 40 consists of zinc and traces of other elements. So, the major component of brass is copper. The proportions of zinc and copper can be varied to create a range of brasses with varying properties. This point is very important. If you are taking or preparing a brass alloy for a particular application, you can vary the percentage of copper and zinc such that there do occur the variation in its properties. Now, brass is not as hard or as strong as steel, but it is harder and stronger than copper. That is, brass has hardness, high hardness and strength compared to elemental copper. So, when copper is converted to brass, there do occur an increase in its strength as well as hardness. This property makes brass easier to form into shape like hexes, tubes, cylinders and for pipes, or this simply implies that you can modify the brass alloy into various suitable forms. Besides these properties, brass is a corrosion resistant and resistant to salt water or saline water also. Now, the aim of the present experiment. We already mentioned about the brass alloy, and the brass consists of about 60% of copper, and the aim of the present experiment is the estimation of copper content. That is, the sharp aim of the present experiment is to estimate the amount of copper in the given brass alloy. For this purpose, approximately N/20, that is 0.05 normal sodium thiosulfate solution and annular potassium dichromate crystals are provided. So, by utilizing these two important reagents, that is 0.05 normal potassium dichromate as well as sodium thiosulfate, you have to estimate the amount of copper present in the given brass alloy. Principle behind the experiment. Annular potassium dichromate, that is K2Cr2O7 crystal, is a primary standard, and this can be used to prepare a standard solution. By utilizing that potassium dichromate standard solution, you can standardize the given sodium thiosulfate solution. Previously, the reagents required, you noted that the given sodium thiosulfate is approximately N/20. So, in order to evaluate its exact concentration, we require a standard solution of potassium dichromate. It is possible with the potassium dichromate crystals because it is a primary standard. You can weigh out it accurately and prepare it into a standard solution. By utilizing that potassium dichromate standard solution, you can standardize the given sodium thiosulfate for its exact concentration. Now, in the presence of acid, hydrochloric acid preferably, potassium dichromate liberates iodine from a solution of potassium iodide. The reaction responsible for the liberation of iodine from potassium iodide with acidified potassium dichromate is shown here. Potassium dichromate plus 6Ka plus 14 HCl produces 2 CrCl3 plus 8 KCl plus 7 H2 plus 3 molecules of iodine. Here you can see iodine is liberated, and as a result of this reaction, potassium dichromate in its plus 6 oxidation state is just reduced to Cr3 plus, and the equivalent mass of this potassium dichromate, which performs as an oxidizing agent in this reaction, is obtained by dividing its molar mass with the change in oxidation number to get the equivalent mass as 49. That is, the equivalent mass of potassium dichromate in the present experiment, in the present reaction, is equal to 49. Now, the liberated iodine during the reaction is titrated with Na2H2O3 solution. Remember, here we are performing the titration with the liberated iodine. Therefore, the present titration is a good example for iodometric titration. You are familiar with iodimetry and iodometry. In iodimetry, we are using direct iodine solution for titration, but in iodometry, we are using liberated iodine. So, the present experiment belongs to the category of iodometry. Iodine oxidizes sodium thiosulfate to sodium tetrathionate. The reaction responsible for the conversion of sodium thiosulfate to sodium tetrathionate with iodine is shown here. 2 Na2H2O3 plus I2 gives Na2S4O6 plus sodium iodide. So, iodine acts as an oxidizing agent in this reaction. So, iodine get reduced to I minus. Since in this reaction, one molecule of sodium thiosulfate reacts with one equivalent of iodine. Thus, it is clear that the equivalent mass of sodium thiosulfate is same as its molar mass. But note that Na2H2O3 is commercially available in its stable form as Na2H2O3 5H2O. That is, sodium thiosulfate exists as sodium thiosulfate pentahydrate. So, the molar mass of sodium thiosulfate pentahydrate is calculated and it is equal to 248.19. Note that this molar mass is same as the equivalent mass of sodium thiosulfate. Using the standardized sodium thiosulfate solution, which is already standardized by using a standard solution of potassium dichromate, the copper content present in given brass sample can be estimated. Copper in brass can be estimated using iodometric titration after dissolving it in nitric acid. So, here also we are performing titration with the liberated iodine, that is nothing but iodometric titration. Copper present in brass is first converted to copper 2 plus. This is made possible by dissolving it in nitric acid. Nitric acid convert copper present in brass into copper nitrate CuNO3 twice that contain copper 2 plus. Copper 2 plus can liberate iodine from potassium iodide solution, and the reaction responsible for such liberation of iodine from potassium iodide solution is 2Cu2 plus plus 4I minus produces Cu2I2 plus I2. You can see copper 2 plus present on the left hand side is just reduced to copper plus 1, while I minus is oxidized to I0, that is, iodine is oxidized to 0 oxidation state from -1 state. So, this is simply a redox reaction. At the same time, iodine is liberated during the course of the reaction, and this liberated iodine can be titrated for leading to the estimation of copper. Here, the equivalent mass of copper is same as its equivalent mass or same as its atomic mass. That means, for copper, atomic mass is same as equivalent mass, and atomic mass as well as equivalent mass of copper is same, which is equal to 63.54. You can see iodine is liberated during the above reaction, and the liberated iodine can be titrated against standard sodium thiosulfate solution, which enable the estimation of copper, or this is used to estimate copper. This reaction is popular and familiar to you. 2 Na2S2O3 plus I2 gives Na2S4O6 plus 2 sodium iodide. In both the titration, that is in standardization as well as estimation part of the entire experiment, starch can be used as the indicator. At the end point of the titration, the blue color produced by the starch indicator changes to a colorless solution. Now we are discussing the reagents required for the entire experiment. The reagents required are depicted here. Annular potassium dichromate crystals, approximately N by 10 sodium thiosulfate solution, brass for estimation of copper, nitric acid, concentrated HCl, 5% potassium iodide solution, starch solution as indicator for the purpose, ammonium hydroxide solution, acetic acid solution, and 10% ammonium thiocyanate solution. These much chemicals or reagents are required to perform the analysis. Now we are entering into procedure behind the experiment. The procedure has 3 parts. The first part is the preparation of the standard potassium dichromate solution. The mass of potassium dichromate, which is a primary standard required to prepare 250 ml of N by 20 solution, can be calculated by using the expression weight required is equal to volume into equivalent weight into normality divided by 1000. In the present case, it is equal to 250 into 49 into 0.05 divided by 1000, and you will get the weight as 0.6125 gram. This means a weight of 0.6125 gram of potassium dichromate made up to 250 ml produces a solution, a standard solution of potassium dichromate with the concentration 0.05 normal. Now, roughly weigh out about 0.6 gram of AR potassium dichromate and transferred it into a dry weighing bottle. It is then weighed by an electronic balance and the weight is recorded as W1. Note that W1 is the weight of sample of potassium dichromate plus weighing bottle. The substance, the potassium dichromate present in the weighing bottle, is now transferred to a 250 ml standard flask through a funnel and made up to the mark. The weight of empty weighing bottle is taken as W2 gram. The actual weight of potassium dichromate is calculated as the difference in weight, that is equal to W1 minus W2. The obtained weight W1 minus W2 is used to find out the concentration of potassium dichromate solution which is prepared. Normality is given by weight per liter divided by equivalent weight. Normality is equal to weight per liter divided by equivalent weight. Now the second part of the experiment, that is nothing but the standardization of sodium thiosulfate solution. We already prepared a standard solution of potassium dichromate and now performing the titration between that standard solution of potassium dichromate with the sodium thiosulfate to enable standardization of sodium thiosulfate. And for this purpose, we are using a conventional titration procedure. 20 ml of potassium dichromate, which is made up, is pipetted out into a conical flask and add 3 ml of pure concentrated hydrochloric acid. About 10 ml of 5% potassium iodide solution is now added and diluted to 100 ml and titrated against the sodium thiosulfate solution, which is given and taken in burette. The addition of sodium thiosulfate solution is continued until the solution is changed to pale yellow in color. At this point, about 2 ml of starch solution is added and the titration is continued until the blue color changes to green. Repeat the titration for concordant values. Now we are demonstrating the standardization of sodium thiosulfate. standardization part of the entire experiment, and now entering into the calculation part. The weight of potassium dichromate taken is the difference, that is equal to W1 minus W2, which is equal to 0.6198 for the present experiment. The weight of potassium dichromate per liter is equal to 0.6198 multiplied with the 4. The quantity 4 is because you are prepared a 250 ml solution. In order to get the weight per liter, you have to multiply with the 4 to get the weight per 1000 ml, that is per liter. That is equal to 2.4792 gram. Now, normality of potassium dichromate solution is equal to weight per liter divided by equivalent weight, that is equal to 2.4792 divided by 49. You will get the normality of the standard solution of potassium dichromate as 0.0506 normal. Now, the calculation continues. The titer values for the titration between standard solution of potassium dichromate and the given sodium thiosulfate can be tabulated like this. The titration is K2Cr2O7 against sodium thiosulfate. Volume of potassium dichromate pipetted out in 3 cases will be same, that is equal to 20 ml, and the corresponding burette readings are shown in the right hand side of this tabular column, and you got the concordant value, that is the concordant value corresponds to the volume of sodium thiosulfate for the present titration will be equal to 20.3 ml. And from the titer value, we can calculate the normality of the sodium thiosulfate solution using the relation N sodium thiosulfate into V sodium thiosulfate is equal to N potassium dichromate into V potassium dichromate. In the present experiment, we already calculated the value of potassium dichromate, that is equal to 0.0506 normal, and the volume of potassium dichromate pipetted out, that is equal to 20 ml, and we got the concordant value, which is nothing but the volume of sodium thiosulfate as 20.3 ml, and on proper substitution we will get the normality of sodium thiosulfate solution as 0.0498 normal. This is the normality of the given sodium thiosulfate solution. With this sodium thiosulfate solution, we are going to perform the estimation. Now, the last part of the experiment, that is nothing but estimation of copper. About 0.5 gram of brass is weighed out accurately and transferred to a 100 ml beaker. It is dissolved in minimum quantity of 1:1 nitric acid, that is 50 nitric acid and 50 water, 50 ml water. So, you are getting 1:1 nitric acid, and the brass sample is dissolved in 1:1 nitric acid. The solution is diluted with 30 ml of water and heated for boiling. Now, about 1 gram of urea is also added and again boiled to 2 minutes, and the presence of urea supports the removal of oxides of nitrogen. That is why we are adding 1 gram of urea during boiling. The solution is now cooled, transferred quantitatively into 100 ml standard flask and made up to the mark. So, now you got a 100 ml solution. 20 ml of the solution is pipetted out into a conical flask. Ammonium hydroxide is added drop by drop till a permanent precipitate is formed. The precipitate is now dissolved by adding required quantity of 1:1 acetic acid. About 15 ml of 5% potassium iodide solution is added and liberated iodine is titrated against standardized sodium thiosulfate solution taken in the burette. The starch is used as the indicator towards the end. The titration is continued until the blue color commences to fade. About 10 ml of 10% ammonium thiocyanate solution is added and then titration is continued until the blue color is just discharged. Repeat the titration to get the concordant values, and from the titer values the amount of copper can be estimated. Now, we are demonstrating estimation of copper. the estimation of copper experiment and now entering into the calculation part. The titer values for the reaction, for the estimation can be tabulated like this. Titration is between copper salt solution and sodium thiosulfate. The volume of copper salt pipetted out is 20 in 3 titrations. Corresponding burette readings and concordant values are noted there. And the concordant value corresponds to the volume of sodium thiosulfate solution, which is already standardized, is equal to 19.7 ml. From the titer values, we can calculate the normality of copper salt, copper solution using the relation N1 V1 is equal to N2 V2. N1 stands for normality of copper solution, V1 stands for volume of copper solution which is prepared from the brass. N2 is equal to 0.0498 normal, that is the normality of the sodium thiosulfate solution which is already standardized. V2 is equal to 19.7 which is the concordant value during the last titration, and N1 is calculated as N2 V2 divided by V1 which is equal to 0.0498 into 19.7 the whole divided by 20, and the final value, that is the normality of the copper solution, will be equal to 0.0490 normal. Calculation continues. The weight per liter can be calculated like this. Weight per liter of the copper in solution is equal to normality multiplied with equivalent weight. You know the fact that the equivalent weight of copper is equal to 63.54. So, you have to multiply that with the present normality. So, you got 0.0490 normal multiplied with the 63.54, you are getting the weight per liter which is equal to 3.1134 gram per liter. Mass of copper in the whole of the given solution is weight per liter divided by 10, that is equal to 0.3113 gram. Now, the mass of brass taken is already noted and that is equal to 0.5112 gram. Percentage of copper in brass equal to mass of copper divided by mass of brass taken into 100. Mass of copper is calculated as 0.3113. Just divide with the mass of copper taken, that is 0.5112, and multiply with the 100 to get the percentage of copper in the given brass as 60.89%. Final result of the experiment is shown here. Percentage of available chlorine in the given sample of bleaching powder is equal to 60.89%. That all about the present experiment. Have a nice learning experience. Thank you.